This is instantaneous rates of change. We're pretty comfortable at the moment finding average rates of change. An instantaneous rate of change is, instead of saying what's the average rate of change between 0 and 2 seconds and finding the slope of that chord, what we'll be doing is saying, for example, for this ball that we've been studying, how fast is it travelling after exactly 1 second? So imagining that we've got our police speed camera gun, and after 1 second we shoot the laser at the ball and see exactly how fast it's going. Okay, so literally at this point, after 1 second, how fast is it travelling? So to get an idea of what this is, we'll look at an example of a hammer throw. So if we watch this guy doing his hammer throw, this ball's got a velocity all the way, it's going around, and when he lets it go, it continues at whatever the instantaneous velocity was. Okay, so basically like in this diagram here, he's spinning around with the ball has an instantaneous velocity at all times. When he releases the ball at that point, that's close. When he releases the ball at this point, at the point of release, it'll continue at its instantaneous velocity, okay, which we can see in this diagram. When the ball goes around, instantaneous velocity will always be tangential to the path that it has been taken. So if we can look at this guy in a little bit of slow-mo, about to release it, lets it go at this point, and the ball goes out in that direction tangentially to where he let it go. And I found this cool clip of the Hulk throwing a truck around. We're going to do exactly the same thing. We can see that the truck goes tangentially to where it was released. So the idea of instantaneous rates of change is I need to be able to draw a tangent line to this curve at the point that I'm interested in and find what the slope of that tangent was. So at this point, t equals 1, my tangent line would be the straight line going in that direction. So from this point, if there was no longer any gravity, this ball would just keep continuing up in that direction, okay, because the instantaneous velocity of the ball at that point was in that direction. And we could do a similar thing down the bottom. The instantaneous velocity at like 3.2 is downwards in this direction. And we know up here is positive, ball's going up in the air. Down here, velocity is negative, the ball's going down. Okay, so I'll get rid of these extra things. We're trying to find what the slope of that tangent line is. Okay, this is called the tangent to the curve. The way we'll do that is using the average rate of change formula, but we'll use it in a way where we are going to essentially get really, really close to this tangent of the curve. So the first approximation we'll make to try and approximate this tangent is to find the average velocity, the average rate of change from t equals 1 to t equals 2. So here's t equals 1, here's t equals 2. I want to find what the average rate of change between those 2 points are, because that's going to be sort of close to that tangent. Okay, so my average velocity will be my average rate of change. I've got this formula for it. I know I can find it by finding the height after 2 seconds minus the height after 1 second divided by 2 minus 1. Okay, we're using h's because my formula here is in h's. And just so that we don't get confused, h of 2 means h when t equals 2. Yep. Okay, so off to the side, I can find what h of 2 is and what h of 1 is, okay, by substituting it into my h of t formula. Okay, so minus 5 times 2 squared plus 20 times 2 plus 1, and I can do the same with 1. Okay, so by the magic of television, I believe h of 1 is 16 and h of 2 is 21. So I can calculate my average rate of change. H of 2 is 21 minus 16 all over 1. I get an average rate of change of 5 meters per second. So my approximation at the moment for the instantaneous velocity at that instant at t equals 1 is 5 meters per second. So I think that I could probably do better than that. I think it's possible to do better. So I'm going to, instead of going between t equals 1 and t equals 2, I'm going to try between t equals 1 and t equals 1.5 and find the average rate of change there, which hopefully will be closer to the tangent. Okay, so again, same deal, average rate of change, h of the biggest one minus h of the smallest one, divided by the difference between these two. Okay, and I can evaluate both of these. So do that yourself, see how you go. So where we're at is I got an average rate of change of 7.5 meters per second there. So as we can see, it's increasing. Okay, the slope is increasing as our chord here gets closer to our tangent. So I'll get rid of these guys. So essentially what's happening here is I'm trying to draw the tangent to this point at t equals 1. So I'm going to put the tangent line on there, and we're trying to approximate that tangent by taking a point at t equals 1 and putting another point a little bit ahead of it and trying to find the slope of that line. So our first approximation was between 1 and 2. Okay, we can see the slope of this line isn't really anywhere near the slope of the tangent, the purple line. So what I'm going to do is, like we did algebraically, move this second point so that it's closer to 1. So I'm going to move it to 1.5. Okay, there's our slope, 7.5. Okay, see how this slope is getting closer to the slope of the tangent, which is our instantaneous velocity. Okay, just demonstrate that again. We were between 1 and 2. We're now between 1 and 1.5. Okay, so what we're going to do in this final section, and this is how we'll calculate instantaneous rates of change, is just go from t equals 1 to a point really close to 1. Okay, say 1.01. We'll always just use 0.01 as our approximation. Okay, and I'll find the slope between those 2 points, which is going to be extremely close to the slope of the tangent. Okay, as we can see on this demonstration, as 1.5 gets closer and closer to 1, watch on the graph, see how the secant gets really close, or the chord rather, gets really close to the tangent. Okay, and I'll give you a link to this so you can play with it, do this sort of stuff. Okay, lots of fun. Okay, so you should be able to calculate the slope of the tangent between 1 and 0.1 Hopefully we're going to get 9.95 or something like that. Okay, but it'll be exactly the same idea. So the instantaneous rate of change, okay, which will abbreviate to IROC, hilarious, will be h of 1.01 minus h of 1 on the difference between those two t coordinates. So again, off to the side, do a bit of hard work. I don't want to spoil this for you, so make sure you have a go yourself. Okay, we already know what h of 1 is. That's been 16 all the time. Okay, have a go at calculating the instantaneous rate of change. Okay, hopefully you got 9.95. And we can see some sort of pattern occurring. This will be our best approximation. That's probably as far as we'll go. Let's look at this pattern. So between 1 and 2, we had 5 meters per second. So I'm going to put that in the table at the bottom. Okay. So the secant or the chord between t equals 1 and t equals 2 was 5. Between t equals 1 and t equals 1.5, it was 7.5. Yeah, that last one we did was 9.95. And then we could go to these further extremes. So 1.001. Okay, I'll get 9.995. I need 4 zeros now. I get 9.99994. Okay, how many zeros are here? 5 zeros. I'll put an extra 0 in here. Okay, hopefully we see some sort of pattern occurring here. Okay, getting really, really close to 10. Okay, and how many zeros are here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is quality TV. Okay, 10, essentially 10. Okay, 10.000. I think it messes up a little bit because of the way computers do calculations. Sometimes the gradient looks pretty weird, but this is pretty much 10. So what we'd write at the bottom as our understanding is, as the second point approaches 1, the slope approaches 10. So when we do these instantaneous rates of change problems, I can notice that this is pretty much 10. So I'd say it's approximately 10 meters per second. Okay, so probably pause this now and have a crack at number 7 and 5C. Probably try question 7 first, because that's pretty similar to the one we did. What's the rate of the depth of water changing after 2 minutes? So I'd look at between t equals 2 and t equals 2.01. Just find the average rate of change between those 2 points. And for question 5, I'm only getting you to do part C. Can I write on this? Okay, we're looking... okay, for 5C, finding instantaneous rates of change at these points. So here's my function. Okay, y of x equals 9 minus x squared. Okay, instantaneous rate of change at x equals minus 2 would be from x equals minus 2 to x equals minus 1.99. Average rate of change between those 2 points. Alright, so what we can actually do as well is use our graphics calculator to approximate some of these things. Okay, so using that same graph we played with, we should be able to find the instantaneous rate of change using our graphics calculator. Okay, we can use this to to approximate and check our answers. So make sure you graph this function. You need to do this by yourself as well. Okay. Make sure your view window is pretty good. I went between -5 and 10 and -5 and 25. Okay, graph the thing, and I want to try and draw a tangent on my graphics calculator. So I've entered into graph mode. Yep, done. Ensure derivatives is enabled in shift setup. So I go shift setup. Where's derivative? Scroll down. Okay, turn on. That's pretty easy. Okay, and I'll draw it, and now shift F4. So I'm sketching a tangent. Okay, and then it'll ask me where I want the tangent. I'm going to do the same one we did in the first example. So I'm going to make x equals 1. Okay, just type the number 1 in your calculator and press exe. Okay, and it'll draw the slope of the tangent. So here is the equation of the tangent line. Okay, and here's the point that we're at. All right, so if you just want to know what the slope is, okay, when you sketch the tangent and type in the value, okay, just press the exe once, and you can see here dy dx equals 10. Okay, that's telling us what the slope is at that point. So I want you to have a go at completing this table, finding the slope or the velocity for all of these points. Okay, so from 0, the slope is 20. Okay, so I'd write that in 20 at 0.5, so 0.5. Okay, slope is 9.75. Okay, I can put that in. The slope at 1, which is the one that we've been spending heaps of time calculating. Okay, the slope is 10, as we calculated on the previous page. And we can do this for all the other points as well. Okay, so you can see how the velocity changes over time. Okay, and if we wanted to, we could draw a graph of this. So we're really spending a lot of time on this one problem, okay, because I want you to have something to link it to all the time. So plot all these points, so 0 up to 4. How am I going to do this? 1, 2, 3, 4. Looks good. 8.5, 9.75, yeah, about there. 1 is about 10. Interesting, maybe that 9.75 was wrong. Yeah, it should be 15. Okay, so to show you where I made the mistake, I accidentally took that y value instead of the dy dx, which is the slope. Okay, 1.5 is 5, 2 is 0, 2.5 is -5, so don't make that mistake. Okay, we should be able to plot how this goes. And we can see the velocity, how it's changing over time. Okay, so this velocity graph versus the height graph, it's pretty much what we expect. When the ball's going up, okay, it's got a positive velocity, so positive velocities when it's going up. At the point t equals 2, okay, the ball actually has a 0 velocity, and we can see that there. The slope is 0, and then after this, okay, after the point 2, the slopes are negative. So the velocity at 4, for example, is -20. Okay, these sort of understandings are going to be really key. I'll try and make this a bit prettier. Okay, and you can draw all over that picture if you want. So positive velocity from here. Positive slope, negative slope, 0 slope, and we can see that here as well. All of this is positive, all of this is negative, and this here is 0. Yeah, that's a really key concept. Okay, so you can use that to check your answers, okay, and to improve your understanding. Okay, the final one is sometimes you're not given the equation of the line, like the Brisbane temperature, and you still want to find what's the instantaneous rate of change. So we've got the Brisbane temperature for 6th of May 2015. Okay, I want to find the instantaneous rate of change at 7 AM. So here's 7 AM, here's the point. I'm going to try and draw a tangent line to it as best I can. So I get my ruler out and try and draw a tangent line. Okay, I want to find the slope of that line. I can do this by just finding 2 convenient points. So I'd take maybe this point and this point. Okay, coordinates of this point are 3, 8. Coordinates of this point are 10, 22. And I'll find the slope between those 2 points. Okay, so instantaneous rate of change. Okay, it's just going to be the average rate of change formula, but I'm using the tangent. Okay, not a random chord. So change in temperature over change in time, capital T, little t. Call this T1, T1, T2, T2. And I'll be able to find the difference between these two. A difference in temperature on difference in time. Okay, and be able to calculate the instantaneous rate of change. So 14 on 7, okay, I get about 2 degrees, okay, because this is degrees Celsius per hour. Which means at that point, the temperature change is 2 degrees per hour at that instant. If we were at a different point on the graph, okay, the slope would be completely different, and our instantaneous rate of change would be different too. Okay, what about at 6 PM? We could do the same thing. It's probably a little bit harder to draw a tangent here, but we can have a go. Okay, about there will do. Obviously use your ruler, do as best you can. Find some convenient points. Those 2 points look good enough. Okay, if we don't have a convenient point over here, there's no problem with me using this point. Okay, so I'll do it in a different color so we can be sure to see it's a different problem. So this point, 18 and 20 will be my time and my temperature 1, correction. And over here 22 and 14 will be T2, T2. Okay, so instantaneous rate of change here. Again, change in temperature and change in time. Again, the difference between the temperatures and the difference between the times. Okay, and let's have a look, -6 on 4. So minus 1.5 degrees Celsius per hour. Okay, does it make sense to be negative? Yep, sure, because the slope of that tangent, our instantaneous rate of change, is going downhill. So there's a fair few problems here for you to practice. Okay, the key points are, if you can draw the tangent, okay, the instantaneous rate of change is just the slope of that tangent using 2 convenient points. Much better is if you have the equation, if you have here the equation of the line. Okay, we could find the tangent just by like randomly drawing this tangent and finding 2 convenient points. Okay, but there's lots of sources of error there, so we'd prefer to just use that formula to find 2 points that are really close and find the rate of change between them. Okay, so I want you to have a go at some of these problems. Okay, on whatever day we have class next, we're going to be going through a heap of these problems and making sure that everyone can do it because it's a really important skill. All right, bye.